Consider our dog scenario. And after a certain amount of time, dog 1 will be at point 1 and dog 2 will be at point 2. Alright, since their corners on a square, they will always be a rotation of pi over 2 away from each next dog. So if the first point was at r theta, the next dog is at r theta rotated 90 degrees. And we are assuming that the pole is right in the middle. Alright, let's find a function that describes the path of dog number 1 this whole time here. We're looking for the function that we could put into our calculator, or decimals, where we enter functions for r, which is a function of theta. Alright, that's our goal. What is the curve that describes the path of this dog? R equals some function of theta. Alright, in class we talked about finding the slope of this vector, as this dog is always looking at this dog, and the blue dog is always running straight toward the green dog, and green dog is always running straight towards the yellow dog, and as the yellow dog moves, he has to move left a little bit. We are going to find the slope of this vector, which is this dog pointed straight at the next dog. Alright, let's find that slope. In class, I alluded to finding the slope 2 different ways. So the first way we'll do it is by just using the slope formula, but that requires rectangular coordinates. So we're going to change these points' coordinates here to rectangular. We know that the x-coordinate is r cosine of theta, and the y-coordinate is r sine of theta. Alright, so P1's xy rectangular coordinates are r cosine of theta, r sine of theta. P2's xy rectangular coordinates will be r times cosine of its angle, comma, r times sine of its angle. Alright, so now that we have the x and y coordinates, we can find the slope. However, I want the angles to be the same. I don't want this angle to be theta plus pi over 2. I want to rewrite it in terms of just theta. So we're going to use a trig identity. We're going to rewrite this cosine as a different trig function of just theta. We know we can do this because the sine and cosine function are exactly the same shapes. They're the same sinusoids. They're just horizontally shifted of each other. So let's take a look at that over here really fast. There's cosine of theta, and in blue is the sine ratio. Alright, so if we have cosine of theta plus pi over 2, that's a horizontal translation of pi over 2 to the left. Where is the green cosine curve if we translate it pi over 2 to the left? Notice that the green cosine curve shifted pi over 2 to the left to this yellow curve is the exact opposite of the blue curve. So, if this yellow curve is now cosine of theta plus pi over 2, we can replace it with the opposite of the blue curve, the opposite of sine of theta. So we have r times a negative sine of theta, or in other words, negative r sine of theta. Alright, now we're going to do something similar with the blue sine curve. We're going to translate it pi over 2 to the left. Here we go. This blue sine curve translates pi over 2 to the left. What happens to it? It is the same thing as cosine. So sine of theta plus pi over 2 is the same thing as cosine. So this coordinate is r cosine of theta. Okay, now let's find the slope doing y2 minus y1 over x2 minus x1. And if we factor out the common factor of r everywhere, the slope is equal to... Alright, now let's find the slope, again, of this vector, the direction that dog 1 is pointing at when they're running toward dog 2. Another way. So what's another way we can find the slope? Well, think of that slope as dy dx. Again, we're finding the slope of the vector of dog 1's direction. So we're going to be using its coordinate, dog 1's coordinates. So we know dy dx is equivalent to the quotient of dy d theta and dx d theta, because if we simplify this just like fractions, the d thetas will cancel out, and it's the same as dy dx. So what is dy d theta? Well, the y-coordinate is right here. And remember that r is itself a function of theta. So we're going to have to use the product rule. Dy d theta, using the product rule of this expression y, is dr d theta times sine plus the derivative of this, which is cosine of theta times r. Now let's do dx d theta. Dr d theta times cosine plus the derivative of cosine, which is the negative sine of theta times r. All right, we have the slope of this directional vector for dog 1 expressed two different ways. Well, if they're both the same slope, then we can set these slopes equal to each other. We will do that next. Alright, I simply set these expressions for the slope equal to each other, and now we're going to solve. I'm going to cross multiply. It's a lot of writing, so I'm going to change sine of theta to just s, and cosine of theta to just c, and r prime of theta. Sine of theta is just r prime s, r cosine is rc. So when we cross multiply, we have s minus c times r prime c minus rs. And in this direction, we have c plus s multiplied by r prime s plus rc. I'm going to go ahead and distribute things and collect like terms. Okay, there's the distribution on the left side. Now we'll do the right side. There we go. All right, let's do some combining of like terms and maybe getting everybody on one side. I see a plus RCS and a plus RCS. I see r prime sine cosine, r prime sine cosine. And that's about it for canceling common factors out. Now let's just combine some like terms or something. I don't know. Let's see. Oh yeah, let's add the red thing, put it on the other side with this yellow expression. Let's subtract the green from the right so that it's over here left with the blue term. And then we can factor out the negative r on this side, the r prime on this side. Whoa, this is working out really nicely because this sum is just 1. So we have negative r equals, and this sum is just 1, r prime. I'm going to switch the order around. So the red r prime equals the blue negative r. All right, and remember what we're trying to find. We're trying to find r. Well, what we have here is a differential equation. We're trying to find r, but we have a derivative of r with respect to theta. So how do we solve differential equations? We'll do separation of variables. So we'll collect the r variable with the dr, and the d theta will go to the other side. And then we'll do the antiderivative. So the antiderivative of 1 over r with respect to r is a natural log of the absolute value of r. And the antiderivative of negative 1 with respect to theta is negative theta plus some constant. A lot of things here from AP Calculus AB last year. All right, we're trying to solve for r, and we're so close. We need to get rid of this natural log, so we'll do the inverse function, which is the exponentiation, same base e. Now we have the absolute value of r is equal to e to the power, which is the same thing as e to the negative theta multiplied by e to some constant. And we'll put that first. But if c is just some constant, then some constant raised to some constant we can just think of as some constant. And that constant might be positive, it might be negative, so we don't need the absolute value signs anymore. Because the absolute value sign meant the right side could have been positive or negative, but if we're just going to have a constant there, that can be positive or negative, so we can just say R. We are cooking here. R of theta is some constant times e to the negative theta. Well, now we just need to find what C is. Recall that dog's position in the very beginning was root 2 away from the pole with a rotation of 90 degrees or pi over 4 radians. So if we have a given initial condition and we know the R value and the theta value, then we can solve for constant C. So C then is equal to root 2 e to the pi over 4. Because if you multiply this side times e to the pi over 4, you'll have e to the negative pi over 4 plus pi over 4, which is e to the 0, which is just 1c. All right, so c is equal to root 2 e to the pi over 4. So now we can rewrite our equation for r as c times e to the negative theta. Or in other words, root 2 e to the power of pi over 4 minus theta. And boys and girls, ladies and gentlemen, this is the curve of dog 1's spiraled path to the origin. And yeah, if you graph that function starting at pi over 4, which is where we know we began up here in the upper right corner, sure enough, gives us that spiral. All right, that was a big problem. This is just for fun. I'll never ask you to do something like that. This is on the level of a Putnam problem, actually. So, yeah, if you followed along through this whole video, on some level I hope that you appreciated it. I wonder if a week from now, you will be able to derive this dog's path from scratch on your own.